Okay.
Okay. So I just wanted to start with that very, very briefly with this comment or question about the exponential long exact sequence bit for abelian surfaces, especially for generic abelian surfaces. So right, the general theme was that when the abelian surface gets generic, it gets a little bit harder to interpret, guess, the exponential long exact sequence. And I was going so far as to guessing that it might end up with a sort of fractal-ish higher Picard group. And you're very doubtful about that.
I just don't know. I was doubtful at first, but I see what you mean. So I want to do an example, but I didn't.
Yes, right. I guess we're not at all ready to do that right now. But I think the situation is maybe sharper and more interesting than I had realized. I mean, I think I have an argument that says that it should have this fractalist nature if this long exact sequence splits up into all these short exact sequences. The short exact sequences to fit in the rows, plus the ultra short exact sequences, including the ones that do the connecting position. So I think this is a straightforward argument that if you only have those kind of direct summands in this long exact sequence of topological abelian groups or something like that, then I think we're forced to get something peculiar for the higher Picard group, something fractalish, co-kernel of a proper dense thing or something like that. But the escape route is very interesting. The escape route is, you just have to show me that there's some longer direct summand that's maybe, length 4 or maybe length infinite or something like that, that would puncture my argument.
So there's the question of where the heck these topological abelian groups really are showing up. That is it really, is that really the category that we're working in, or does it just sort of look like that?
Yeah, I don't know, because that's right. That's something sounds to me like an exact category, or I don't even know what an exact category is, but the kind of category where you should talk about exact sequences living in it.
Yeah.
So
that's one thing that you've mentioned before.
Right. We're committing all sorts of sins.
But then there's another thing, right? So if it's really in the category of abelian groups, am I confused? But in the category of abelian groups, doesn't something about the homological dimension of Z mean that they're there's a limit to how long? Maybe I'm confused.
No, that sounds right. For abelian groups, well, but wait a minute.
I may be making some stupid mistake, but
no, that sounds right.
So is it true that, let me just say it, right? So something like the homological dimension of Z is low enough so that that every long exact sequence can be written as a kind of overlay of exact sequences that have at most 3 non-zero terms in them. Is that?
Yeah. That sounds right.
Yeah. So so that would.
Right, in that category, it must decompose, as you say, into pretty short pieces if it's abelian groups. But maybe the topology that we're unsure about, maybe that topology really is somehow screwing it up, complicating it, making things get more entangled. And so I'm very curious to see how this works out when we explore the examples, which I don't want to do right now, and it sounds like we don't want to do right now. So so my plan for today, right? So is my topic the Jugendtraum? Have I been saying that my topic maybe should be called Artin reciprocity and the Jugendtraum?
Okay.
Or maybe it should be called From Artin Reciprocity to the Jugendtraum.
Right.
And I'm trying to make it sound like a narrative, like, there's a progression here. But it could be just a very personal progression for me. Maybe I'm doing it the wrong way. I can imagine somebody else who might go the other way around, from the Jugendraum to Artin reciprocity theorem. Right, different realizations seem like culminations or climaxes, depending on which order you learn things in. So it could be that the way I'm doing it is very dependent on the order in which I learned it, or the order in which I think you should learn it, or something like that. So there's all sorts of possibilities here. But like last time when I was talking about all these different levels of understanding, I realized at some point that I'm trying to put these levels of understanding into a narrative, into a story form. And there's supposed to be one sort of big climactic aha moment when you leap up to the next level. And that's the level when you go from my point of view, it's when you go from the Artin reciprocity theorem and up to the Jugendraum. So the Artin reciprocity theorem sort of sets the stage for the Jugendraum to appear. And when it appears, it's a very dramatic moment. But I don't think we're going to get to that dramatic moment today.
Great. Okay.
Because I'm going to take a certain approach to talking about the Artin reciprocity theorem today. And in fact, that approach to talking about the Artin reciprocity theorem involves really talking about something else. So I've in the last couple of days, I've been really getting interested in this idea that there are really interesting analogies between Artin reciprocity theorem and Kildren's drawings. And in a way, this is really, really, I mean, the germ of that idea is very standard stuff. I mean, right? I mean, that, Galois theory has a geometric interpretation in terms of covering spaces, and from the very beginning, when I was learning about the Galois theory of number fields in terms of reciprocity laws and stuff like that, I was always very driven by, analogies to the whole story of fundamental groups and covering spaces.
Yep.
So that shouldn't seem like a surprise. That should seem like we're just revisiting old ideas. But I think the thing is that for me, when we do this Kildren's drawing stuff, I think we're not just doing the same old story of the relationship between the fundamental group and the and covering spaces. I mean, what is the basic story? What the covering spaces are sort of the actions of the fundamental group, the G sets, where G is the fundamental group. But one reason the children's drawing story is more interesting than that is because of the branch points, the ramification of the covers. So that's certainly, but we've already got some ideas. Right?
Yeah, that's already present in the Galois theory story of the relation between Galois theory to covers.
Yes, that's definitely a big part of it. But I just meant that it's not already there. It's not already in there when I just first started learning about fundamental groups and covering spaces. I learned about unbranched covering spaces, and then the idea that you should fit branch covering spaces is in there somehow. That really seems like it's going beyond homotopy theory. But maybe if you do homotopy theory at a sophisticated enough level, you can actually see how the branch covers are playing some sort of conceptual role in there. I'm not sure. I'm not going to worry about that too much at the moment. But there's another way in which the children's drawings has an extra ingredient that I don't think I was really ready to appreciate before until maybe just this year or something like that. And that is just the whole business of the holomorphic structure. And the idea that I think I have a lot more understanding of things like, how these children's drawings, they live on curves. These curves are projective complex varieties. These curves have Jacobian varieties and stuff like that. So I think
I
this is
thought
gonna,
you were going to say something else,
okay, what were you going to say? What do you think I should say?
which is that,
Yeah.
so in these children's drawings, at least in their basic form, you're looking at covers over the 3 punctured Riemann sphere, and then there's some kind of fundamental group of that. But but then the Galois group of the rationals winds up acting on the set of children's drawings. So I don't understand this terribly well, but the Galois group is not acting as deck transformations of a specific covering of.
Yeah, I don't think I started really thinking about that until like about an hour ago when I was getting ready to come. Okay, that's a very interesting theme, but yeah, one of the reasons I didn't say anything about that is because I didn't start thinking about that until like an hour ago. You know, I mean, one of the things you're pointing about is just that these children's drawings things, I guess maybe the whole point of them from a certain viewpoint is that, you know, they're not just living over the complex numbers. They're not just holomorphic. They're like rational. They were living over the rationals in some sense or something like that. Did I say that right? I mean, I'm not sure I said that right, but they have a lot to do with, like you said, the Galois group of the rationals and stuff like that. The way Baez theorem works. It does say something about any curve that's, what's the word, defined over the rationals? Is that the right way to say it? I'm sure I'm saying that right. Anyway, I'll worry about that later.
I thought it was even defined over an algebraic
extension
of the rationals.
Maybe that's what it
different? Is. Yeah, but yeah,
Or maybe I meant, you know, not defined over, but weakly defined over. I don't know, but defined very far over. Yeah, well, I just think that, you know, my understanding, I'm hoping that my understanding of branch covers of complex projective curves is more sophisticated or better or something now than better developed, and particularly that it goes beyond just thinking about the fundamental group and the homotopy theory of the fundamental group, how it corresponds to covering spaces. We'll see how it goes. But yeah, so I'm going to try and make some analogies here between the Artin reciprocity theorem and children's drawings. And so that sort of gives me an excuse to maybe be even more unsystematic than last time. But I'm really going to try to work these examples, work these analogies. So let me try to, on my paper here, let me try to set up, you know, sort of 2 sides of the paper. And one side will be Artin reciprocity for number fields. And the other side will be children's drawings or whatever the name is, dessins d'enfant or something, children's. No.
Have you tried making puns about children's drawings and then the Jugendtraum? It's like a Jugendtraum a little later in the development of the kid.
I think I somehow totally missed that. All right, that's a very good point. Yeah, I mean, these 2 title column headings or whatever, they don't seem exactly parallel. Maybe it should be number fields on one side and children's drawing, or complex projective curves on the other side. I don't know. We'll see. So yeah, when I say that I'm approaching this very unsystematic, I mean that I'm really making even less of an attempt than last time to actually state the Artin reciprocity theorem as a theorem. I'm just going to start acting it out in certain cases, and then try to act out corresponding things with children's drawings. So there are various examples that I like to use a lot of the times, like when I'm dealing with number fields. It's actually much better to use lots of different examples, but I'm falling back on my usual example just to avoid getting caught in making all sorts of mistakes. One of my usual examples is the 20th cyclotomic field. Which has an automorphism group, which consists of, well, I mean, there are what? There are 20th cyclotomic field, that's about the 20th roots of unity. Out of the 20th roots of unity, there are just 8 of them that are primitive 20th roots of unity. That's probably counted by some numerical function called an Euler-Tauschen function or something like that, counting the number of primitive something or others.
Things that are relatively prime to 20.
Yeah, yeah.
And less than 20.
Yeah. So those are the primitive 20th roots of unity. The 20th cyclotomic field is sort of the walking primitive 20th root of unity. So you can take, your favorite primitive 20th root of unity to any one of the 8 of them. So there's an 8 element automorphism group there, which, let's see, how do I draw this? This is very bad. I'm obviously not taking advantage of all the built-in line drawing things on this. So let's see, the factors of 20 are, the prime factors of 20 are 2 and 5. And there's another prime lurking around here. Arguably, there's another prime lurking around here that plays some role, which is the prime that Conway calls -1. But I've written a sort of 2-dimensional picture. So at the moment, the role of the prime -1 is somewhat suppressed in this picture. But what am I trying to say here? That how does this work? Let's see. So we have what is it? 1 and what am I trying to say? Oh, it's actually right. This is, the prime is 2, but it goes into 20 twice.
Good. So did you get the letters 2 and 5 backwards, the number?
Did I?
Or no? I don't know. It depends what you're trying to do.
Right. It depends on what I'm trying to do. I'm trying to write, so, there's 2 squared, and there's, so 2 squared is 4, and GL1 comma 4, GL1 comma Z mod 4 is just the 2 elements 1 and 3 that are relatively prime to 4.
Okay, no, you're right.
And GL1, did I say that right? GL1 comma Z mod 4, yeah, is 1 and 3. GL1 Z mod 5 is the 4 elements, which I'm never quite sure what's the best order to write them in. I guess I'll try 1, 2, 4, 3. Those are the powers of 2. So 2 is like a primitive something or other. It's a generator of the group. And so what happens? So yeah, I'm trying to fill out these, fill this out with the numbers that are less than 20 and relatively prime to it. Let's see, there's 17 and 7 are both 2 mod 5. Is it like this? Am I doing this right? Yes, because 7 is 3 mod 4. And 9 and 19 are both 4 mod 5. So I think it goes like this.
Mhm.
And 3 and 13 are both 3 mod 5, and they're, yeah, mod 4, they're that way. So this is actually this automorphism group, this Galois group of this field. It's a kind of Galois group. And I mean, all groups are Galois groups from my, and well, one of the roles of these numbers is that they actually represent congruence classes of primes. So sometimes it's convenient to have actual representatives, prime representatives of these congruence classes, mod 20. And it's just convenient, right? I mean, I just like this example that in the teens, you just take 11, 13, 17, and 19, and that gives you the representatives right there. And for the other ones, you just go from 100 to 110. That's also, that has the same property, right? So it's like 101 and 107 and 109 and 103. That's just if you want to have actual prime representatives. So these are all actual primes that represent these congruence classes. And yeah, so we've got 3 primes or 3 points, right? Prime and point are sort of synonyms for each other. So we've got 3 points here that are playing some role. So in our, so
what are the 3 primes?
2, 5, and -1.
Oh, okay.
So in the children's drawings, we've also got 3 primes or 3 points or whatever you call them. So I'll have like 0. Well, so we have, okay. Over here we have 2, 5, and -1. So over here I have 0. Well, sorry, I had to get to be a Q. 0 and 1. Oh, that's supposed to be a comma, I guess. 0, 1, and infinity. And I am sort of thinking of them like that. I don't know why I'm lining up that way. I'm thinking of 0 as being like 2, 1 as being like 5, and infinity as being like -1. I mean, especially I'm thinking of infinity as being like -1, because I don't know, right? There is sort of like
any reason more than it's like the weird one?
it's the weird one, but yeah, no, that's the reason. But also they sort of act like check bits, checksum things or something. You know what I mean? You're like, maybe that will maybe that will make more sense later on. So so let me try to do some example here. So actually, I mean, I should actually draw the exact same table, well, the exact same shape table that I drew in the left-hand column. I should draw that in the right-hand column. In some sense, I should, but I'm not going to do it that way. I'm going to do a slightly different example that I happen to have already done. So I'll do something like.
So is the game that, like in this,
yeah,
right-hand one, you could draw any quotient group of something like the cartographic group or the free group on two generators or
Okay,
something?
so it's going to be the free group on two generators.
Uh-huh.
It's going to be the free group on two generators, which we're thinking of as the fundamental group of the thrice punctured plane. But right, one of those punctures we think of as really big. I mean, right, I'm thinking of this thrice punctured plane as being like the figure 8.
And you're using plane to mean sphere?
What did I say?
You said thrice punctured plane, but I think you meant
Oh,
thrice
okay,
punctured
yes, okay.
sphere.
Thrice punctured sphere, yes.
Uh-huh,
That's
yeah.
right, that's right.
Uh-huh. You can get away with calling a sphere a line.
Right.
You can't get away with calling it a plane.
That's true, that's true. Yeah, but I mean, I was just, mentioning, thinking of this as a figure 8 to dramatize the idea that infinity is the weird one. Infinity is the big puncture on the outside of the figure 8, and 0 and 1 are the two little punctures that are like the loops of the figure 8. But what did you say? I mean, I was about to. I think you said something that I was going to.
Oh, I was wondering if you could actually if you actually remove those punctures and get different coverings of the thrice punctured sphere.
Yeah.
We could have different fundamental groups.
Yes.
And I was wondering if you could actually get the same group that you had over on the left.
Yeah, we can.
Chart if you wanted to like really ham it up.
Yes, yes, and I do want to ham it up, but I'm actually going to ham it up in a slightly different direction before I ham it up in that way. Okay. So actually, there's several examples that I'm. Yeah, there's at least 3 examples that I really can't make up my mind between yet. So first of all, okay. So how are we going to draw these things? So first of all, we're just going to draw them as finite sets with pairs of permutations on them. So these are finite G sets where G is the free group on two generators. So you can just draw them by drawing the elements being acted on, just draw them as like dots. And then by means of 2 different colors of arrows, draw 2 different permutations on that set of dots. And I have a feeling that, well, ideally, I would really like to get to a non-abelian example today, even. I mean, if we don't get to it today, we'll certainly try to get to it other days. But I'm really, really trying to do the, I mean, Artin reciprocity is all about abelian extensions of number fields.
Mm-hmm.
I mean, that's almost exactly what Artin reciprocity theorem is about. It just almost tells you almost everything you want to know about abelian extension of number fields, everything in some sense.
Mm-hmm.
So that's motivating me to focus just on abelian children's drawings. So that just means that the 2 permutations should commute with each other.
Mm-hmm.
And that basically means that they all look like rectangles. Yeah, I can just draw these things as rectangles. That's what these abelian children's drawings really are like that. I mean, we're going to want to, right? I'm not at all good yet at taking one of these rectangles and turning it into an actual child's drawing. But we certainly want to be able to do that. I sort of have some ideas about how to do that. But let me draw a couple of rectangles that that I think maybe we should use, but they're all good for different purposes, but I can't really make up my mind which one we should do. So, I mean, there's this one, which is motivated just by the fact that, as you say, we're just hamming it up by using the exact same rectangle that we had in the, so maybe we'll have this be 0 and this be 1. And then infinity will sort of be the checksum digit or something like that. But another one we could use would be this one. This one's kind of interesting. I don't suppose you want to take any wild guess about why that one's interesting. And then there's also this one. Which is interesting to me because I did some fun calculations with it. Let me tell, right. So the one on the left is fun because it's hamming up the analogy to the left-hand column.
Mhm.
The one in the middle is fun because it turns out to be a famous complex projective curve. I guess I'll maintain the suspense about that for a little while as to what famous complex projective curve that is. The one on the right is just interesting because I had some fun working out some details of it. So I think that's when I'm going to actually start, just so we can have some fun working some stuff out. So right. So let's make it clear how we're thinking of this as a rectangle. So I'm thinking of, usually I think of it as like dots as being the set, but here it's the set of boxes in the rectangle. That's the set being acted on. And I guess do we have a name for this action? Maybe it's the Frobenius or something. Is that what I should call it? That's probably what the name is in a certain context, but I'm not trying to understand how that concept works well enough yet to really call that the Frobenius. I'll just call it, well, do you have any suggestion what should I call it? This is, it's supposed to represent, it's just a certain path in the fundamental group. So yeah, it's a path that starts at the base point and then it travels around zero. So you didn't make anything mystical out of the fact that the infinity symbol looks like a picture of the.
I was restraining myself. I decided I was like saying too many silly jokes. Yeah. But when you said figure eight, I couldn't. I couldn't help but think of
again,
that.
I'm missing half of the jokes here.
Yeah.
So what does that mean? Oh yeah. Well, maybe we should. That'll be sort of like zeros in the middle there, and one is in the middle there, and maybe that's 1/2 or something. I don't know. At the intersection point of the figure eight. I don't know. All right. Yes. So again, I mean, right. I always when there are like when there is two dimensions, I always get confused. Right. It's the usual thing I always complain about. That the x-axis is where y.
Yep.
Is what?
0.
Y is 0.
Right. Yeah. Now I'm trying to remember the time when it's like with Coxeter groups that we could get really confused about that.
Yeah, there's a whole bunch of things like that, right? And particularly when you just have two things, it's easier to get confused than when you have more. So I could easily get myself in trouble there, but I think I'm sort of correct in associating, 0 here with that the action that's associated to 0 going around the loop that goes around 0. That's the horizontal. Because I wrote 0 on the horizontal thing there, and I wrote 1 on the vertical thing there. So I think we should think of, cycling around horizontally as going around 0, and cycling up and down vertically as going around 1. So let's try to you know, so yeah, I mean, so, you know, right? I mean, we're sort of taste, you know, we're I don't know, there's millions of ways of saying it. We've got this action of this group. So we've got this homomorphism from free group on 2 generators into this 12 bang. And the image of that homomorphism is this Galois group that you were talking about, or is that what you call a deck transformation group? I don't know, but we're going to try to, you know, we're going to try to see this curve and everything like that. So, so got my infinite scrolling here. Hopefully that's right.
Oh, stop showing off.
Have we emphasized that not only do we have, not only do we have infinite scrolling, we also have what? Infinite. Actually, I haven't tested it, right? Do we have infinite zooming?
Do you have infinite horizontal scrolling?
Yes, but also infinite zooming. I'm saying we have infinite zooming.
Yeah, zooming out.
And zooming in.
Yeah. Okay. Can you zoom out a lot? Could we like shrink this whole thing down to like a speck, and then you could like draw some enormous?
Probably, but that's a good question.
I mean,
you know, I'm not trying. I'm trying not to annoy the guys too much because I don't know what will go wrong if I do. But
yeah.
But it's kind of fun. Well, right, it would be kind of fun if I started zooming in and zooming in and zooming in, and it'd be fun if all of a sudden it wouldn't let me zoom in any further. But I don't know if that will happen.
So you could put commentary on things that's like really tiny compared, sort of like in the Talmud.
Say that again?
Sort of like in the Talmud, you could put commentary in much smaller letters.
I'm not sure I'm familiar with that tradition. But
they would sometimes have these little midrashim, little comments on around the edges of the Talmud.
And is that deliberately so that the uninitiated wouldn't be able to read it, or the people with bad eyesight wouldn't be able to read it, or people with good eyesight wouldn't be able to read it?
Yeah, I don't think so. Yeah, that's backwards. Only the old people should. Okay. Anyway, so I'm beginning to get the idea of this stuff.
Well, I mean, is it clear? I mean, right? This whole relativity of sightedness there. I mean, the people with who are that really nearsighted people who are used to studying that, they would consider that, you know, the good eyesight is the ones who can take off their glasses and just look at that.
That's true.
But
okay,
anyway.
So that's good. The old scholars should be able to like read the really small comments.
Well, there's a lot of problems with that, but okay. So how do we do this? So, well, okay. Let me just remind myself of what the Galois correspondence looks like on the left-hand side. So it looks something like what? Like
I'm not going to draw this thing again. I have it in my notebook.
Sure.
From when you drew it.
Sure, I'm not being very efficient here, but
yeah.
So let's see. Galois correspondence is contravariant, so the big one should be at the bottom. I mean, big one is the small one. That's the small field, but the big group, small group, but big field is at the top. And then there's all sorts of patterns here that make it somewhat easy to remember how this works. I just put in the cyclotomic ones. This is like 4th cyclotomic. Well, again, okay, I have to point with my cursor. This is where the 4th cyclotomic one is. This is the 5th cyclotomic. This is the 20th cyclotomic. This is the 1st cyclotomic. Let's see, there's this one here. There's this one here. this is a complete list of all the subgroups arranged in a hierarchy. And this one is here, and this one is here. I think that's it. And the containment relations are, it might be a little bit not what you're expecting. So, I mean, these two ones in the middle, they are very connected to a lot of others. So like, what am I trying to say? Well, there's, well, first of all, right, the top one contains all the others. Top field contains all the other fields. Bottom field is contained in all the others. But, or maybe I should just talk in terms of subgroups instead of subfields. I mean, it's the same thing. So let's see. So this subgroup, this 2-element subgroup, it's contained in all the 4-element subgroups, right?
Mm-hmm.
And this 4-element subgroup in the middle contains all the 2-element subgroups. So it's like that. And I hope that's sort of readable. And that's like all the containment relations. So, those ones in the middle are very good at connecting to others. There's ones on the periphery are more peripheral. Okay, so we're trying to do the same sort of hierarchical picture of all the subgroups for our other one, our 3x4. So how does that work? So I've got 3x4. So that's just there. Well, so I think this is real, right? So this is really, I've drawn it as a rectangle, but it's really just, 3 and 4 are relatively prime to each other. So this is really just a Z mod 12 as an abelian group. It's really a cyclic abelian group. So the subgroups should just be the factors of 12, I think. So I think it's like, this right? I mean, what are those? So how many factors of 12 are there? There's 6 factors of 12. 1, 2, 3, 4,
6
and 12. 1, 2, 3, 4, 6, and 12. Okay. So I think they're sort of arranged like this.
So this is like the divisibility poset capped off at 12.
Yeah, I think so.
Yeah.
So yeah, big subgroup is at the bottom. So yeah, it's the subgroup lattice upside down. And let me just try to cheat by referring to some of my paper notes here so I can. Pictures here. Some pictures here. Okay. All right. So there's one like this. Is that right? And then there's one like this. And there's one like this. Doing this right.
Looks good. There's 6.
So it's like this, like this, like this, like this. Like this, like this, and then the one more containment relationship is and that doesn't prevent it from being a lattice. I mean, maybe that even helps it be a lattice or something like that. I guess I don't know much about lattice theory in that sense.
Yeah.
Subgroups of a lattice, subgroups of a group should form a lattice.
Yeah.
This looks like all, unless I screwed up, this is all the subgroups of that group.
Is it a distributive lattice?
I don't think so.
Okay.
Is it?
I don't know.
It shouldn't
Probably.
be, right? It
Probably.
should be a modulo of that. Well,
okay. There are these like, yeah, okay. I guess it'd be more. There are these like famous theorems like saying like,
yeah,
something will be like a modular lattice if it doesn't contain any
that's true.
Hasse diagrams that look like this. So you seem to sort of like be hinting at like, oh, this looks like almost bad for being a good lattice, but
yeah. So what? Right. What?
I guess it's not.
Well, it should have right. You brought it up, so I'm now forced to have a little bit of fun with this. So you're telling me I should be able to find the non-distributive one here. So what's that? Do I really? You know, there's the one that has top and bottom and then 3 in the middle. Maybe you're telling me this really is distributive. Oh, okay. Maybe you're right. Maybe this really is distributive.
Well, yeah, I was just, you mean just because of some peculiarity of this particular, I don't know any. So like, yeah.
Maybe
so
it's obviously, maybe the stability poset thing you're talking about is more distributive than I realized. I was thinking, you know, subgroups of an abelian group in general, that'd be like a modular of lattice, right? I don't know. But yeah, there's fun stuff here to waste time on, but let's not. I mean, I did start wasting time on it, but you talked me out of it. Okay. So.
I acted too enthusiastic.
What?
I acted too enthusiastic.
Well, it was just
like if you start walking and the dog starts charging ahead, like, wait, I'm not that interested. Yeah, I'm not that interested either, but
okay.
I used to know some of those theorems.
It's actually probably, yeah, there's all sorts of secret reasons why that stuff is more interesting than you might even guess. But I should restrain myself from. Okay. So it sounds like I'm claiming that we have these 1, 2, 3, 4, 5, 6 children's drawings here, or these 6 complex projects, Bellier curves, whatever you call them, these things. We have 6 complex projective curves here, allegedly. I mean, this is all based on complete, well, unless I actually learned this stuff and then forgot that I learned it. A lot of this is based on guesswork. So as usual, it could be all sorts of mistakes here.
But for these cyclic covers, which is what these kind of covers are, I mean, I think, can't we just sort of like say that, like, can't we like write down an equation for the curve that's like,
yes, I think so.
I am almost tempted to tell you what it is, but if that's what's
how about
show, then I won't.
Well, no, but let me give you a different example to tell me. Why don't you tell me this example then, the one that I claim is a famous example?
Yeah, so I mean that's part of what tipped me off, but so that seems like that should be like y equals x squared. This might not be what you meant at all. It looks like,
yeah.
I want to get a curve that has like a branch point of order 2 at the origin.
Yeah. Yeah.
And so and then a branch point of order 3 at 1.
Right. And you want to do it by doing 2 completely separate extensions and they're both the simplest kind of extension. Just this cyclic extension between 0 and infinity, and then this other cyclic extension between 1 and infinity. And you want to just, so we're doing a little, geometric pullback square or algebraic push-out square. I'm agreeing with you. I mean,
Yeah, okay.
Yeah.
I'm getting confused somehow, but
Let's try it. Let's try
it should, I mean,
Yeah.
it should, I think what you're hinting at is that it should be like connected to like the moduli space of elliptic curves, so that like squarey and cubey, like this branch is like two different kind of branch points of order 2 and 3.
Let's try to work it out. So it's like we're saying we have our original coordinate function, I'll call it x. And then we have a new coordinate function, which is, don't tell me, the square root of x. And another new coordinate function, which is the cube root of x minus 1. Or perhaps vice versa, or something like that.
Mm-hmm.
So, we can call this like y, we can call this z or something like that. But now, can you sort of simplify this and tell me what famous elliptic curve it is? Did I say it? I already gave away that it's an elliptic curve. I mean, what are we saying? We're saying we've got x, and we've got x, y, and z. And we've got two equations, one of which is y
squared equals x.
Say it again, y squared equals x.
Yeah.
And the other one is what? Z
cubed
z
equals
cubed
x minus 1.
z cubed equals x minus 1. Okay, so can you either recognize either what?
Yeah, I don't know why I'm so confused. I want,
Well,
so
you
now
just
it's got-
eliminate the variable x. How about that?
Oh, that's probably what was confusing. Okay, that sounds good. So then,
yeah, let's try that.
okay, no, that makes me happier. So then,
But we should have done. Can't. I mean, it's not too late to change it now, right? Can't I just put the cube thing over? Sorry, I'm screwing up here. I don't do that. I put the eraser is on, and then I erase that. Oh, I'm not very good at this. Is that so close you can't erase it?
Connected.
But it's not. It's not. Okay, see, I did it, and then I put the cube over there. Okay.
Really?
And now I have to change these others too, right? So what do we say? The eraser. Erase that. Oh, so you don't even have to touch it. Okay. And then, sorry, was this too much screwing around? So what is it? Y cubed equals x? Did I screw it up? Maybe it was already perfect and I just screwed it up. What is this?
What I don't like is that now, I mean, I don't know if this mattered that much to you, but it looked like that you wanted, when you went around the or twice, you got back to where you started from, and you went around one thrice, you got back to where you started from. That's what that rectangle, I thought it said. Although maybe I was misreading that rectangle.
Oh, no, you're probably right. I mean, okay, so yeah,
if you wanted to,
yeah, maybe I rotated my rectangle by 90 degrees. I don't know. Let's be sloppy about this part of it, and let's just get. So what equation do you get when you?
Okay, now given
x?
what you've got, I would take the last equation there.
Yeah.
Where I see the x in there, I'd write y cubed.
So I get z squared.
So yeah, I see what
you're y cubed minus 1. And I think that's pretty much a famous elliptic curve.
Yeah.
Which is
yep.
Yeah, so it looks like this, yeah. Again, we were very sloppy about rotating the rectangle by 90 degrees. Maybe I made some other silly mistakes or something, but I think this should work. And again, it looks something like we could have got all these rectangles or something like x to the a plus y to the b equals 1 or something like that. I'm not sure I did that exactly right, but it's probably something like that. And I didn't even think about what happens if we try to put in, this, instead of having, right, there's something going on here where, right, you need two poles, right? You can't like do a monopole unwrapping or something like that. So, we've been using the weird one, infinity, as the extra, the checksum bit, right? There's like a conservation law or something going on here. And like I say, I use the weird one as this, garbage pail that, to sweep all the annoying ramification that we need. So, but I mean, right, we could also have something that was just ramified at 0 and 1 and did it in an abelian way. And I didn't even think about those yet, but those, yeah, I just didn't get around to exploring those yet, but right, but yeah, I think all these rectangle ones that we're talking about are just these, these x to the a plus y to the b equals 1 or something like that. Yeah, so when we chose a to be 2 and b equals 3 or something like that, then we got a very familiar example. But in general, it should be, well, I mean, that one that one's so famous, we know the genus is 1. But right, so it would be like, I probably don't have right at my fingertips the answer to what is the genus for all these rectangles in general, but there's probably some simple formula for figuring out the genus, right? But rather than just guessing the genus numerologically, it'd be a little bit nicer to have something a little bit more systematic about, taking this pair of permutations and doing something with it, right? I mean, there's the Chanuel interpretation of the Euler characteristic, which is really probably just the original Euler interpretation of the Euler characteristic, where it's very V minus E plus F-ish or something, but with more curvilinear potato-shaped things. What am I trying to say? That, if you knew right, there are these anomalous fibers. If you knew exactly how many points are in this anomalous fiber, exactly how many points are in each of the 3 anomalous fibers, and then you knew, how many depths there are over the non-anomalous part, then that gives you a very straightforward Euler characteristic calculation, which determines the genus. So, right, it seems like the key thing is figuring out what the anomalous, what's the size of the anomalous fiber is. So in other words, we want some way to take this finite set with this pair of permutations on it, and we want to be able to figure out, I think, again, I'm doing this by guesswork, but it seems like there should be some rule. It seems like from any one of these pairs of permutations, we should be able to get a children's drawing. Even if it's not a being, we should be able to get a children's drawing. And there should be some nice, relatively simple combinatorial rule for figuring out what the anomalous fibers are. And I don't actually have a complete understanding yet of what the rules should be for that in the general non-abelian case.
Sorry, what are the anomalous fibers in this? What do you mean?
What do I mean by the anomalous fiber?
Yeah.
So you know, the children's drawing gives us a covering space. The covering space has this projection down to the original thrice marked Riemann sphere.
Yeah.
And those 3 marks are the special points where the projection may be somewhat singular-ish. So in other words, those are the 3 anomalous fibers, the fibers over the 3 marked points.
Okay, but in this particular case, it seems like we're pretty much saying what we want the behavior to be at 0 and 1. Namely that it's like the Riemann sheets of like the nth root function.
Yeah.
At those 2 points. And then, so then well,
but still to figure out what happens at infinity.
Yeah, sorry, right, yeah. Mm-hmm.
Well, so what I was going to say is I would like a simple combinatorial rule that, you know, let's just take any one of these finite actions of the 3-on-2 generators and turn it into a children's drawing, but in particular, tell us, you know, what the 3 anomalous fibers are. And I didn't really come up with, I made a sort of obvious conjecture. I made what I thought was an obvious conjecture about how to do it. And then as far as I could tell, that obvious conjecture didn't really work, but it did seem to work in the abelian case. So like you're also suggesting that in this abelian, this rectangle case, at least, that it's sort of relatively obvious, relatively easy to figure out what the anomalous fibers should be. Let me tell you what my...
Yeah, except at infinity, which probably I should be able to figure out by this sort of principle of like infinity is the slop bucket.
Wastebasket? Wastebasket?
The wastebasket for extra. And I don't know exactly what that means, but yeah, there's some kind of conservation law that forces that to do what it has to do.
Yes. Well, so let me say something about that. So, I mean, we've got these 2 generators, you know, going around 0 and going on. But then we've got this other non-generator, which consists of, right, going backwards around 1 and then going backwards around 0. And, you know, that's the thing for going around infinity. Right. You know, going backwards around 1 and then going backwards around 0, if I said it correctly. Or, you know, if I used the right convention or something like that, I think that's the way it should work. And so the silly obvious conjecture that seems to be false, but that I made the conjecture anyway, was something like, well, you have these 2 permutations, but then you get the 3rd permutation by what we said, right? You just take the composite of the inverse permutations. And for each of those permutations has a set of orbits. And I just conjectured that those set of orbits were the fibers. You know, so the fiber over 0 would be the orbits of the action by 0. I have a feeling that, well, like I say, I think this conjecture, as far as I can tell, this conjecture seems to be false in the general case, unless I did my calculations really good. But it seems to be true in the abelian case, I think, or I'm just on the basis of wild guessing, you know, checking, very careless reasoning. It seems like it's probably true in the abelian case.
So like the total number of sheets of the cover is just the number of in the rectangle in the abelian case.
Yes, yes, yes.
And then there are
That-
these two commuting actions on that set of sheets.
That's right. That's right. So yeah. So for this Eisenstein elliptic curve example, we've got 6 boxes in the rectangle. So that's 6 of the non-anomalous sheets, 6 of the generic things. And those generic things count as -1, right? I mean, that's, if you check it out, those count as negative. Those count as negative. So it's like a -6 plus the positive things for the 3 anomalous fibers. And it looks like the action by 0, well, the action by one of them has 2 orbits. The action by the other one of them has 3 orbits.
Yeah.
And then the action by the composite, or the composite of the negatives or whatever, has just 1 orbit, because 2 and 3 are relatively prime.
Right. Yeah, so that's gonna work out differently in the first example.
That's right. That's right. That's right. But isn't that like some famous little glitch that we like tried to figure out one time, that when you take like y squared equals a cubic, you get an elliptic, you get genus 1. But when you take y squared equals a quartic, you also get genus 1. And yeah. I think that's making sense, exactly because of this wastebasket at infinity.
I don't get that. That'd be interesting.
Well, I'm saying, okay, let me try and get it to work. So is this working? So yeah, I'm not sure if this is going to work, but let's try it. So I mean, you see how we're getting -6 plus 3 plus 2 plus 1 equals 0. That's 0 Euler characteristic for the, that's genus 1, right? That's for the 2 by 3 rectangle.
Let's see if I understand slow down and say like what the heck you're doing there. So you're calculating the Euler characteristic.
So it's negative the total number. Yes, we're calculating the Euler characteristic. Yes, by, the bulk counts as negative. And like you say, there are 6 sheets for this 2 by 3 rectangle.
So what's the rule for getting the Euler characteristic that you're using?
It's that a how do I say this?
You get like +1 for each.
A thrice punctured sphere, an unpunctured sphere is Euler characteristic 2.
Mm-hmm.
So thrice punctured sphere is Euler characteristic -1.
Mm-hmm.
And that's the bulk. So that's why I'm saying the bulk, the sheets, count negative. So you're saying there's 6 sheets, those count negative.
Each one gives you a -1. I see.
Yes.
Okay, I see. Sort of. Yeah. This is this is like the Riemann-Hurwitz formula. Yeah. Or something.
Let me write that down. Let me write that down.
Maybe that's the wrong name for it. What is it?
Well, but I'll write it down anyway. Question marks.
It's a.
Because I didn't know that that's what I was doing.
I think actually that is what I think you're doing. Yeah. It's a formula in general that relates the Euler characteristics of the 2 guys involved in a branch cover. The guy on the total space and the base. Yeah. But, and yeah, and I finally understood it. And that it is sort of, well, luckily Wikipedia has a decent article on it where they like give like the quick way you guess how it works. And it's sort of like this. So you like take the,
Yeah.
Yeah.
I mean, the fact that
first like
Hurwitz's name,
remove the branch points.
yeah, yes,
Yeah,
yes,
and then you
yes.
get an answer.
Yes.
And then each branch point, how does it work exactly?
I'm also being sloppy about whether the so-called sheets are actually separated from each other. That shouldn't even matter, but go ahead, yeah?
Yeah. So in our example here, you're starting out with a -6.
Negative 6, yes.
And then for this branch point of order 2, what are you doing? You're adding.
If I understand what you mean by order 2, then I'm adding 2 to that. Yeah, -6.
2.
Yeah. For the one of order 3, I'm adding 3.
Okay.
And for the wastebasket, I'm adding 1 because, you know, the fact that 2 is relative apart to 3 means that going down the diagonal, you know, makes everything all in the same order.
Okay.
Okay, so two 2 by 3 rectangle gave us order characteristic 0, which is genus 1. Let's try a 2 by 4.
Okay.
So we've got -8 plus 2 plus 4. But now 2 and 4 aren't relatively prime. So going down by the diagonal, I think it's going to give us, yeah, it's going to give us 2 orbits. So it's -8 plus 2 plus 4 plus 2, which is 0 again.
0. Okay.
So right, this is this, you know, calculation that we've done various times, but it still, you know, slightly confuses me. The fact that when you take a square root of a cubic, you get an elliptic curve, but when you take the square root of a quartic, you also get an elliptic curve. Right? I mean, this is just the fact that our naive guess here is successfully reproducing this fact that, you know, cubics and quartics give the same thing. What do you call the next ones? Quintics and sextics. Those give the same thing, etc. And it's because of this little thing about the wastebasket. That, you know, it's got 1 or 2 orbits depending on whether the other side is divisible by 2. I'm thinking one of the sides is 2 and the other side and the other is some, you know, a 2 by n rectangle, depending on whether n is even or not. The wastebasket thing will be 1 orbit or 2 orbits. So I'm saying that, you know, some things are working out relatively nicely here. So let's try to do this example here. So what do you think of the genuses for the top one?
Sorry, I'm confused.
Yeah.
So that top one there, that's the one-fold branched cover. That's a one-fold branch cover. No. Yes, or is it an 8? Sorry, I kept getting mixed up. So
This one right here, that's what we're talking about?
yeah. So that means that
Yeah.
the group is
That should be
very,
a 12-fold branch cover.
okay,
Yeah.
sorry, yeah, okay. Group
Is
of
that right?
things-
When
I don't know.
yeah.
So
Yeah.
I'm getting all confused. So the group of,
Yeah, I think this
group
is a
of-
stabilizer subgroup. Is that right? That's
Okay.
that's what the Galois correspondent is. It's sort of like a stabilizer subgroup. Yeah.
okay. Okay. So then that's the max, that's the maximally
Yeah.
cover, that's closest to being a universal cover, so to speak, along these.
Yeah. Yeah. Yeah.
So, okay, so that is our curve we were just talking about.
Well, I mean, I was mostly doing examples where it was 2 by n. This is 3
okay.
by 4.
Okay.
Yeah. So I seem to be getting -12. Do you want to do it yourself, or should I say it?
No, I finally realized something. Okay, yeah.
Yeah.
Your way of describing this stuff is sort of different than the way they're saying it in the Wikipedia article on the Riemann-Hurwitz formula, but I see now that it's like it adds up to the same thing. Okay. So anyway, so -12, and then plus 3 plus 4. Am I right so far?
Yes. Yes.
Yeah. Okay. And there's just one orbit of that thing.
Agreed.
So what does that mean? +1?
Yes.
Plus 1.
Yes.
So it's 8 minus 12 is -4.
-4, and that's the Euler characteristic for genus 3? No. Yes, genus 3. Yes, genus 3. That's what I think.
Okay.
Do you agree on that, Gene? So in other words, I think that, this children's drawing lives on a. That's horrible. Sorry. Let me do that again. Damn. I hate that so much. I got to get better at using this. This is still coming out horrible. Okay, and then. So there's some children's drawing that lives on there. I don't think I actually got as far as figuring out exactly what the children's drawing is that lives on there. But yeah, so let's see. So this one down here is obviously just.
Why do you say it lives on there? I thought that these children's drawings would all be on this Riemann sphere, and then they would give these covers.
I don't think that's right.
Wow.
I don't think that's right.
I'm confused.
Okay, the way I thought it works. Okay. Again, I'm just taking silly guesses here. I could have everything screwed up, but the way I'm imagining it is, you've got this covering projection that's branched just at the 0, 1, and infinity in the codomain, and you draw 0 and 1, and you draw the unit interval between them.
Yeah.
Or some other convention or whatever. But I'll think of the unit interval between 0 and 1, and just take the inverse image of and you make 0 and 1 two different colors. I guess maybe made them black and white or something like that. For some reason I tend to draw them as green and red. But you just take the inverse image under the covering projection. So it's an inverse image. So it's right. So the The codomain is of the covering projection. The covered thing is the Riemann sphere, but the inverse image lives on the covering, not the covered. So that's the way I'm imagining this game works. Am I totally screwed up? I think that's the way it works. And then there may be some very special case where I get really confused about whether there's this tendency for, does the genus always tend to get bigger as you cover the more? Is it like sort of monotonic or something? Because are there lots of interesting ways for the genus 0 to cover genus 0?
Sorry, are there lots of ways for genus 0 to cover genus 0? Is that what you said?
Yeah.
I guess there must be, and maybe that confused. That's why I was.
Is that what the trees are? These, because I know, the people talk about there are children's drawings that are trees and ones that are not trees. Is there some simple relationship between the genus and whether it's a tree or not? Or how much of a tree, how untree-like it is? Is that the gene? I don't know.
There's a lot of stuff about this on Wikipedia. It says simplest bipartite graphs of the trees. Any embedding of a tree has a single region. Therefore, by Euler's formula, lies in a spherical surface. It sounds like what you're.
Okay. Don't give away too much of it. You can cheat, but don't give away too much of it to me yet. Let's see. So look at my little table here, okay?
Yep.
So this one over here, that one looks to me like it, comes out to be just a 2x3 rectangle because you're modding out by this little thing over here. So I think this really comes out to be an elliptic curve. So I think, I think this is the Eisenstein elliptic curve over here. And then all these others just come out to be a 1x(n) rectangle or an n×1 rectangle, I think. So I think all of these are genus 0, I think. And, so I'd like to see, I'd like to practice on a whole bunch more examples of this. I'd like to see the actual children's drawings, see if the prediction of the genuses is correct. And I'd like to work out the ramification. So what am I trying to say? Let's go over to the left-hand column for a minute, okay? Let's try to think about where the ramification is. So again, we've got the ramification at 2, ramification at 5, and ramification at -1. So the ramification at -1 right? There's some sensible reason why that has to do with what? With whether the number field is like real or complex or something like that.
Yeah, so I've heard.
So it's like, let's see, the golden integers is right in the middle here. The Gaussian integers is over on the left over here. And the, square root of -5, that's over on the right. So it seems like, all right, I'll put a little red dot where there's some ramification at -1. Isn't that right? Sorry. So there's some ramification there, ramification there. So that's right, that's where it went from real to complex, real to complex. Here it's still real. But let's see, then here, right? That's going from the golden field to the fifth cyclotomic field. So the fifth cyclotomic field, that's definitely complex. And I guess this one is also.
Yeah.
But this one over here, this is the real part of the 20th cyclotomic field.
Yeah.
Oh,
Yeah. So that's still real.
yeah, so that's going there.
So
Okay.
that's nice. So any path from the bottom to the top goes through just one red dot, which is.
That's right. That's right. And that happens precisely when what? Don't tell me. That happens precisely when, let's see. Again, I have to interpret this little wastebasket thing here. What am I trying to say? You should be able to tell it just by looking at the subgroup. What am I trying to say? Oh, I'm not sure how to say it exactly. Let's do the others. Let's do 2 and 5. So let me use some color. I'll use green for 2. So
so those should be easier to tell.
Yes, it should be like, what am I trying to say? That
sort of like, are you removed? It can be both. It can be both. So when you,
well, I'm gonna try to do it just by looking at the subgroups, right? It should be like, what am I trying to say? It looks to me like, I mean, right, if I remembered how to do number theory, then I should be able to just think about these, you know, like square root of -1 and see, oh yes, that's obviously, you know, the Gaussian integers is obviously ramified at 2 or something like that. But I mean, this one seems to be ramified at 2 because, right, it was 2 columns, now it's only 1 column. I mean,
so
does
you're
that make
getting
sense?
rid of some of the horizontal
Something like that.
extent of.
Yes, something like
So when
that.
I was asking you if it's both, what about, like, so the one in the middle would not be green.
The line in the middle is not green, right?
But in the one on the right, is that green?
I think it is.
I think that's green too, yeah. So like if your next color is going to be blue, then it seems like that one there is like also blue as well. That's what I'm wondering, if it could be both.
Okay,
it looks
blue.
like you're getting rid of some verticalness and some.
Yeah, no,
horizontalness.
that's good. That's good. See, because what you're saying is that on this path, we took care of all the ramification, or we took care of a whole lot of the ramification at all 3 primes at the first step, which means that this next one up here
can't do anything.
Is going to be ramification free. So this is going to be the case where the ideal class group is non-trivial. That this thing over here has a non-trivial ideal class group because
that's cool.
Because, yes, it is very cool. It's going from here to the middle thing here.
Yeah,
it's also an unramified extension. Yeah, go ahead.
Yeah, I don't remember that theorem, but what was cool, the other cool thing is just like when you go up there, you notice that like no column is getting fewer x's than it had. No, that's not true. I was going to say that's not true. I was going to say no column gets fewer x's and no row gets fewer x's. But that's not really true.
But something like that. I'm not sure I'm saying it right, but something like that is, you know, you're supposed to really think in terms of this visual thing that you're talking about.
Yeah.
About.
Yeah.
I mean, it has to do with, so like this thing over here has a lot of correlation between the rows and the columns. Right, all the others are sort of, well, no, this one here has a little bit of correlation between rows and columns.
Yeah.
But all these others, so that's, I'm guessing this one here is unramified at blue and green. But let's see. Well, okay, let's see if we can figure out. Again, I'm being very unsystematic here, but.
Oh, I know what I wanted to say.
Yeah, go ahead. Go ahead.
So this, that edge that we were just talking about, where you're going from the. I wish I could point at these damn things, but anyway,
Sure. This
the
one
one
here?
you're, yeah, that one there.
Here. Yeah.
So you'll notice that if you look at the column going through the identity element of your group, without having two x's in it, and it still had two x's in it. And if you did you understand that, what I said?
Say it once more. It sounds like I should try to understand what you're saying. Say it again.
So if you look at the column going through the identity element of the group, which is like the upper.
Oh, the column.
left.
Yes. In up here or down here?
Well, like starting
Either
down
way.
below. Yeah,
Yes.
starting down below. And then
Right.
you go up, you don't lose any x's in the column.
That's
And you also
right.
don't lose any x's in the row.
That's right. So
That's sort of what's,
that's right.
those
So
are the two features that tell us whether we're supposed to put a green or a blue dot in, is whether you lose x's in the column or in a row.
that's right. And I can sort of paraphrase what you said by saying that the progression of going from here to here is sort of like what I sometimes call the downward decorrelation. That I just remove the correlations between horizontal and vertical while making sure that it's getting smaller.
Uh-huh.
The subgroup is getting smaller.
Yep.
And that's I didn't explain very well what I meant by that, but it's there's no correlation between horizontal and vertical anymore, and we did it in a sort of minimal way.
Yep.
So let's just try to do this a little bit more on the left-hand side, and then we'll try to do the same thing on the right-hand side. It should be easier on the right-hand side, right? It should be more geometric and everything. So
yeah, just put in so like down near the bottom, the middle edge should have a blue dot on it, down at the bottom of the picture. Go down. That, I think that's just blue, yeah. Because you're just losing x's in the column.
now I have the feeling that, like you say, you assured me that any path hits the red exactly once, but I think we want to hit the blue exactly twice.
Yes, I guess you're right. Yes.
And we want to hit the green exactly once.
Right. Yep.
So.
Yeah, why don't you just label all the rest of them? I mean, it's not that much work.
Well, yes, but why don't you help me? Because
I'm glad to help you. The trouble is I can't, if you point at one, I can tell you what it's doing.
Well, I'm taking a wild guess that there should be a green here. Is that right? Because we didn't have a green here, so I'm trying to compensate for that.
You're just completely cheating.
Yes, I'm completely cheating.
Wait a minute. Yeah.
Oh, okay. You don't.
Yeah. Okay. Yeah. No, so green means you're losing x's in the row. That is the row through the identity element. So we did lose.
That's right.
Two x's in the
That's
so
right.
and blue means you're losing x's in a column. So that one's just green. Yep.
Okay.
So that one there's no way you can lose any x's in the row. You can only lose it in the column. So
I mean, it sounds like you're telling me there's a blue over here. Sorry, that was supposed to be a blue. Why did it come out green? I was trying to switch to blue. Sounds like you're telling me there's a blue right there, right? Because it's got.
Yeah, losing it in the column. Yeah.
Yeah. And you're telling me there are blues there and maybe here you're telling me there's a blue?
No, you're not losing any blues in the column there.
In the column,
Any
okay.
x's in the column.
Okay.
No, and you're not losing any x's in the column or the row. It's just the red dot there. That's it.
Okay.
Yeah. And then there's a green to the right of the one you just marked.
The green there?
You're only losing it.
Okay, yeah, I agree. I agree there's a green there.
And you didn't, the two on the
there
second.
Was a blue here?
Blue means you're losing it in the column. Yes, there's a blue there. And there's a green in the other one there.
Green. Just a green?
Just a green. Wait, no, it's a green and a blue. Wait, no.
That might be right. Because you do need a lot of blues, right?
Oh yeah, it is. Yeah, no, sorry. Yeah, green and blue. Yep. So yeah.
I mean, we could still have easily made a mistake here somewhere, but we're trying to arrange it so that I think everything should hit 2 blues. Everything should.
Pass should hit 2 blues, a red, and a green.
Yeah.
Yeah, and it looks like it's right. It's sort of cool how there's one edge there that doesn't have anything on it. Yeah, and so that's an unramified. So what's this thing? An unramified cover. It's got to have a non-trivial ideal class group.
Something like that. And yes, well, I mean, we'll have to really try to understand that when we try to really understand the Artin reciprocity theorem. Yes. Ideal class groups have a lot to do with the Galois groups, and the Artin reciprocity theorem should be telling us how to understand that. So, right. I mean, I'm being completely weaselly here about the Artin reciprocity theorem. I'm saying we're acting this out, and that if you actually understood all the things we're acting out here, then you would understand the Artin reciprocity theorem and understand how it's analogous to the children's drawings type thing.
Well, hopefully someday you'll become less weaselly about it, because
absolutely
sounds interesting. Yeah.
Absolutely. But can we try to do the ramification things for the geometric one here, the children's drawings?
Sure. Now you can call them like 0, 1, and infinity or something.
Yeah, I put the green and blue and red.
Oh, okay. Okay. I was hoping you just write 0, 1, and infinity. Half the work in doing this calculation was remembering the color coding system. Okay, but now that I see it up there, I guess I can do it. Okay.
All right, I'll write 0 in green, and I'll write 1 in blue, and I'll write infinity in
okay,
red.
good for the colorblind among us.
Yes. So what's going on?
Okay, so horizontal is, last time you like switched it on me. But so horizontal is like ramification in this around 0, and vertical has to do with it.
That's what I think. Yes.
Yeah,
That's what I think.
Okay.
So
I'm set to go. I'm ready to, except for the infinity part, which I don't understand.
Okay. So tell me about this one.
Okay. So you're losing a bunch of x's in the horizontal.
Yeah.
Which means something about 1. So I think you should just put a blue dot there and not a green dot.
A blue dot. Oh, and a blue dot is a 1?
Oh, okay, a blue 1. Yeah, okay. Yeah, so you're the only one. Redundant coding system here. Yeah.
Okay.
And then the other choice.
Maybe I should I put an index that says, it's by a factor of 2 or something like that? Or it's by a factor of 3.
3. Yeah, okay, now this is more, slightly more exciting. Yeah.
Okay.
And then the other one is a 0 sub 2.
0 sub 2. Okay. Oh, wrong color. What is it?
Oh, you shouldn't. I didn't want you to use these colors. It's like a check bit that only trips you.
Okay. And now.
Got to point at an edge. That's the only thing I can't do. Pointed at an edge that we're going to determine the nature of.
Well, you know what? So I think, we're sort of lucky and or unlucky in that this whole example you see none of these correlations. So in some sense, that means the ramification at infinity is going to be boring. I'm not sure exactly what boring means, but it's going to be in some sense boring because we didn't have the exciting thing about the correlations that we had over on the left-hand side. But we can easily do other examples with children's stories where we will get correlations. That was just, that was one of the reasons this is a insufficiently general example here. So we don't see the correlation phenomenon going on. So yeah, okay. Well, we're aiming for 6:30 quitting time. So we're doing good here. But
so one of the fun things that you didn't mention,
go ahead,
is that you could take one of these pictures that you, well, you did mention it, but I don't want to, you didn't yell it. So you could take one of these pictures, like on the, like this big picture on the right-hand column.
Yeah.
And you could like reinterpret it as a picture on the left-hand column.
Yeah.
So we get
well,
like
I don't completely understand that anywhere well enough yet. But
I mean, you have to pick some primes to do that, but we've picked like 2 and 5. And so once you do that, then somehow like
I don't know what to say about that yet. I'm not sure I understand that well. But one of the things that you're, I think, secretly alluding to here is Baez Rosetta Stone, with one big column. Again, I don't know whether Rosetta Stones, do they have columns or do they have rows? I don't know. Maybe they have columns. But one big column for like maybe global fields, one big column for local fields. But then there's like a really important column that's like more of the, thing that helps mediate between them. What is that? What am I trying to say? I mean, there's finite fields, there's function fields, there's number fields, and there's other kinds of global fields. Maybe there's 4 columns or more columns or something. I don't know, but there's this. Right. So one of the ways that we can really try to, I mean, we've been suggesting that there's some sort of analogy here. Now you're bringing up the issue of, really trying to make this analogy into a genuine analogy or something better than an analogy, make them special, both special cases of some same thing or something like that. And again, this has a lot to do with Baez Rosetta Stone. So did the Rosetta Stone, did that originate in Baez's letter to his sister? Is that where he started talking about that?
It could be. It sounds like where he was like trying to explain math to his philosopher sister without getting too technical or something.
I always get confused. Are there 2 different people named Simone Weil?
No.
No?
Well, I mean, there probably are, but
he is the famous one.
Yeah, his sister is the famous.
All right, I get confused about that, but okay.
Famous philosopher one.
Okay,
yeah, she's really good too, in a very different way.
Okay.
Different way. Okay. But
so yeah,
he didn't actually like draw a chart of the sort that you're alluding to, did he?
I thought he used the word Rosetta Stone.
Yeah, I think you might be right. I mean, he also made allusions to like the quotes from Hindu philosophy of like, when you attain nirvana, you understand everything, then it's lost its charm for you. So like when the analogy turns into a strict set of theorems,
yes,
then it's like no fun anymore. It's lost its bewitching quality.
Well, for me, that takes a long time. So
yeah, I don't think he thought he got there for that one, but
yeah, so it's really good that you're bringing this up. I don't think anything terribly intelligent to say about it yet.
Okay, yeah, I mean, it could be.
But in a way, you also brought this up. This is sort of the same thing that you were trying to bring up way at the beginning of the conversation too. weren't you something about?
Yeah, I think so. Yeah. Anyway, I'm like, it seems like it could be really fun to do because you could like get stuff about number field extensions from branched covers.
Yeah, I also have the
Or vice versa.
I'm very unsure how this should go, but I have the vague feeling that thinking about this analogy, this Rosetta Stone, all of this stuff should have a lot to do with trying to understand what motives are really about. But maybe I'm wrong about that. Maybe that's not really what motives are about. But I have a feeling that it is connected. Do you have any particular response to that?
I just don't.
I don't know.
I mean, if you were doing the case that's more like the curves over finite fields case, that should be like the complex curves case. That I think it was like a very motive.
Well, I thought you were already
idea.
really hinting. I was hinting at that. I thought you were already also really hinting at that.
I wasn't trying to. I was just saying that, like in this case, you could take stuff about curves and translate it into stuff about, or like get pictures like this for curves and send them over to curves for number fields. That's what we're doing right here. So I wasn't getting curves over finite fields into my story.
I mean, I was sloppily blending them all together. I'll have to think more about that. But what was I trying to say? I was going to say something else, but I forget what it was. Let's see. Well, so right, we're running out of time here, but I'm sort of declaring victory here where I shouldn't declare victory, right? There's a whole lot more to work out in these pictures that we're drawing here. Draw these surfaces, draw the actual children's diagrams on these surfaces, understand them in all sorts of ways. Yeah. Another really important thing right here is that, right, we're getting only a very restricted special case of the child's drawings. We're only getting this ridiculously simple case so far of the abelian child's drawings. And that's just so ridiculously simple compared to the general thing that you might be totally unimpressed by that. But one of the games that you can play here is that you can iterate, that you can take any one of these abelian child's drawings, like this one at the top here, it's genus 3 or something like that, and you could use that as the base for further abelian extension. So you could have relatively abelian children's drawings. Given any particular children's drawings, you can look at other children's drawings that are relatively abelian above it. And that should be really interesting. Partially because that should be really interesting because, over on the left-hand column, that would be a little bit analogous to, instead of just Kronecker-Weber theorem, which takes abelian extensions of the rationals, you could take any field that you get as an abelian extension of rationals, and you can use that as the base for further abelian extension. And that has a lot to do with the Jugendtraum and stuff like that. Right. Like if you start taking abelian extensions of the Gaussian field or abelian extensions of the Eisenstein field. So there should be a lot of, right? Don't just you may want to iterate this process of taking abelian extensions. And so, right, so one of the ways to learn a little bit about non-abelian extensions is to iterate taking the abelian extensions. But I mean, that's probably the definition of solvable extensions. Now, there are also very interesting non-solvable non-abelian extensions. But nevertheless, you may be able to learn something very interesting about general-ish non-abelian extensions by studying solvable extensions by studying iterated abelian extensions. I'm still trying to remember what I was going to, I forgot something. I forgot I was going to say a moment ago. I'm still trying to remember what it was, but maybe I'll try to ignore that for now and go on and try to say a little bit of other stuff. So what am I trying to say here? So let me draw a sort of non-abelian alleged child's drawing, but I'll draw it as a pair of permutations. Again, working on the working assumption that you can do that. If I just draw an arbitrary pair of permutations of a finite set, an action, arbitrary finite action of free on two generators. So that should be more or less what a child's drawing is. So for example, I could take 3 points. And I could have one of the two branch points, like let's say 0, act sort of horizontally. But have the other one act sort of cyclically. And so it sort of seems it sort of seems like we should be getting 3 bang as the effective group here. Yep. And this seems this seems like it should be a nice, really very simple basic example to explore. But I mean, right, you could do this with, we could also do examples like, take 17 points and have one of the two generators act, cyclically around all 17 point circle. Have the other one just be a transposition. And that would generate all of 17 bang. So the effective group here would be 17 bang. So what children's drawing is that? And what are the anomalies?
17 because of its famous
Oh no,
roll and
no.
Okay, good.
I don't think I was.
Good. Okay.
I was trying to pick a random number and I failed. I mean, you always fail when you try to pick a
wasn't random enough. Yeah. Okay.
Yeah. None of them are random enough.
Yeah. Dihedral groups. Well, that's right. That's not never mind. Not dihedral groups. This one was also a dihedral group. The other one you talked about is like not the whole permutation group. Yeah.
That's right. That's right. That you generate the whole permutation group just by a transposition and a cyclical thing. Like I say, I'm not even sure I have a good idea of how to get the anomalous fibers in that case. So don't tell me the answer on that yet, okay? Because there's probably something ridiculously simple. But my first conjecture was just take the orbits, and that didn't seem to work. Maybe it does work, and I just screwed up the calculation somehow or something. But but if there is some simple combinatorial rule that's different from my first guess that does work, don't tell me the answer yet. Let me go home and think about that, because I have some silly ideas about what it might be, and I want to test them out before I give up. So, all right. So we're really supposed to be wrapping up now. But I'm still struggling to remember whatever it was I was going to say before that I forgot to say. But I'm also struggling to just think of punchlines to end today's discussion with. So And maybe that is what I was trying to say before or something. But I'm just trying to say that, yeah, I'm probably trying to address this accusation of being weaselly, that I mean, we're being very unsystematic. We're being very example oriented. We're just playing with toy examples. But again, I'm claiming that secretly everything that you really might want to know about the Artin reciprocity theorem, if you continue playing the kind of games that we're playing here, it really leads to a general understanding of the Artin reciprocity theorem. And that will set the stage for this later sudden leap towards the Jugendraum. Well, by the way, so that sort of, I mean, now that I started thinking about it this way, this sets up a big question for me. I mean, I've got Artin reciprocity. What the hell is this pen doing? There's the Artin reciprocity, and I've got the Jugendraum. And they're related to each other. Like I say, I always claim that the Artin reciprocity theorem sets the stage for the Jugendraum. Although I don't know if that's historically accurate. It could be that, you know, other people, other historical progressions may have gone in the opposite direction. But for me, it very much makes sense to think of Artin reciprocity as setting the stage for the Jugendraum. But today I'm talking about how Artin reciprocity is analogous to this whole child's drawing stuff. I mean, maybe I shouldn't call it child's drawings. Maybe I should call it complex projective curves or something like that. But I mean, it raises this question for me of like, what is there? And maybe there's some obvious answer, or maybe there's nothing there. I don't know. But this is a question that I'm suddenly starting to think about.
It sounds like you sort of said that like Artin. Wait, is Artin reciprocity supposed to work for like abelian extensions starting from an arbitrary base, or just from the rationals? I guess it's for an
from an arbitrary base. Yes,
yeah,
an arbitrary base.
Okay.
Except I wasn't sure how arbitrary you meant.
Well, just like a number field.
Yeah, but it's probably more general than that. I don't know how. But well, certainly abelian extensions of an arbitrary number field. Yes, okay. Certainly Artin is supposed to include that. Certainly.
So what is Jugendraum supposed to include according to you? Because there's like one version where it's just like something like abelian extensions of a imaginary quadratic number field. That's like, I think, the one that.
Yes, but there are more general versions, more general outgrowths of the Jugendraum that deal with abelian extensions of I'm trying to remember the jargon, something like totally imaginary number field, which includes things like the rationals and includes things like you know, an imaginary quadratic, but it also includes like every cyclotomic thing I think is totally.
So it's covering less ground than Artin reciprocity, but it's going further. That's
right. It's giving something much more explicit. Now, if I really understood the Artin reciprocity, then maybe the Artin reciprocity. I mean, the people who really understand the Artin reciprocity theorem, maybe they understand how to interpret that in an explicit way. But I'm very suspicious of that, because if the Artin reciprocity theorem was itself so explicit, then what would you even need the Jugendraum for? I don't know.
Yeah, no, that sounds right to me. I guess there could be like other kinds of explicitness, but the kind.
Yeah, there could be different kinds of explicitness.
But I sort of buy that. So then your child's drawings is supposed to cover something And then the question mark might be like covering less ground in it, but becoming more explicit in some way. Is that
Yes.
okay.
Yeah. Yes. I mean, that's what I've been playing around with. Yeah,
Uh-huh.
I've been playing around with trying to imagine what could go there. So, I think we're pretty much done, but I still have the feeling, well, I always have the feeling that there are punchlines that I forgot to deliver. But well, I mean, Artin reciprocity theorem, there are so many viewpoints that we should really try to understand. Like, for example, there's this concept of the Artin symbol, which is presumably an outgrowth of the Legendre symbol, which is this sort of Fourier analysis approach to quadratic reciprocity. Quadratic reciprocity. So yeah, there's a whole bunch of viewpoints toward Artin reciprocity that we should try to appreciate. But that's not exactly what we're trying to do today. What we're trying to do today is to understand that at a very intuitive level, how this Artin reciprocity theorem really should be, morally deserves to be treated in some way that really involves that really can be unified with this whole theory of complex projective curves. So yeah, I mean, there's right. I mean, ideals are important in the Artin reciprocity theorem. That probably means that divisors of something are important with complex projective curves. I mean, even that's just a wild guess on my part at this point, but there's a lot of indications of how we should proceed in trying to understand how to unify, how other people have presumably unified all these things into bigger pictures. So yeah, I'm probably forgetting all sorts of things that I meant to say, but I'll just have to quit there for today. So anything else before we quit?
Nope.
All right, so thanks a lot. This was very helpful. I'll see you.
Okay.
Okay, bye.
Yep, bye.